So we've now spent some time with the van der Waals phase transition, and we've used one rectification approach to tell us when the system, given a particular pressure, will assume the volume that it has in the liquid phase and when it will assume the volume that it has in the gas phase. But that rectification approach missed something important. Typically, when we apply a given pressure and temperature to this system, it will actually have some particles in the gas phase and some particles in the liquid phase. And we know this from just our experience in the world. For instance, boiling a pot of water and having some of it be steam and some of it be liquid water all at once. Today, or I should say in this video, we'll look at a way that we could maybe capture some of that behavior. So what I've done here is I've drawn two full curves for the liquid phase and the gas phase. In other words, I've written one curve that's P liquid and a second curve that's P gas. Now notice that for any P in this range of interest, we'll have one solution for volume for the liquid phase and a different solution for the gas phase. And I've drawn them both here. This orange region that I've labeled in here is the region where we'll never actually have volume in that region. And I want to again point out that this is just a curve for one particular temperature. And the temperature must be low enough that we have these two phases in the first place. Okay, so here's the sort of statement. Now, we could consider a system that simply had this volume to pressure relationship that was always in the liquid phase. And similarly, we could consider a system that was always in the gas phase. And each of those would have an always concave up Helmholtz free energy, and therefore a well-defined Gibbs free energy. So let's see what happens now. We'll have some Gibbs free energy in the liquid phase. It will be a function of P. It will be a function of T. And we'll have some solution V liquid. We know that from before. Oh, sorry. And then we'll have some number of particles. And then on the other side, we'll have G for the gas phase, also a function of the same PT and N. Now, the Gibbs free energies for a given PT and N for the liquid and gas phase will not necessarily be the same thing. However, we can say the following. The two systems will share well, they'll have the same temperature. And that's simply because we're assuming that these systems are touching each other, literally in space. For the same reason, we'll assume that they have the same pressure. So temperature T, pressure P. And this is where I should have been more specific, sorry. The particle numbers will not necessarily be the same. However, because these systems can trade particles, so if we were thinking about water or something like that, water can be kicked from the liquid water phase into the gas phase, into the steam phase, or kicked back. Particles can go between the two phases. So what is the same between these two systems if they're in equilibrium? Well, it's exactly the chemical potential. And this is maybe one of the first times that we'll see chemical potential rearing its head in a very natural way. Great. Now, there is something to note. Well, first of all, let's just write down the system of equations here. So really we just have TL, if you want, is equal to TG, PL is equal to PG. We don't really need to write those down because we've already set them to these constant values or these similar values P and T here. But at the very least, we can say mu L of T P and then NL is equal to mu G of TP and G. And then supposing that we're in a system where we know the total number of particles, we have that NL plus NG is equal to N total. The problem, of course, is that this system of equations in general will be very hard to solve. It won't be something that we can easily do, certainly. However, we can at least say one thing that's very useful to us. Remember that the Gibbs free energy satisfies a very special property. We spoke about this in the video in which we defined the Gibbs free energy for the first time. And that's that because it only has one extensive coordinate, natural coordinate, n, it's actually just equal to n times the chemical potential. So in this case, we have that GL is equal to NL times mu L, and G sub G is equal to N sub G times mu sub G. Good. But if these two objects are the same, so if we set them equal by definition to mu, then notice that G sub L is equal to N sub L mu, and G sub G is equal to N sub G mu. And this implies that G sub L over N sub L is equal to G, oops, let's keep our consistency here, is equal to G sub G over N sub G. Excellent. And now we can state a very important fact, which is that if we assume that we're at some sort of point where we're going from mostly liquid to mostly gas, that is to say, when the number of particles in the liquid phase is equal to the number of particles in the gas phase, then GL is equal to GG. So NL equals NG implies GL is equal to GG. Good. Now this seems innocuous. Maybe it seems helpful in some limited context that we can just equate the Gibbs free energies in this case when we're switching from mostly liquid to mostly gas, but it's actually even better than that. So over here, let's remember that GL is equal to F is equal to FL plus PVL, and GG is equal to FG plus PVG, where the P's are the same in both cases, because again, we're assuming that these are at the same pressures. And GL is equal to GG exactly when these two things are equal. But the astute among you will notice that this is exactly the same criterion as the point when we switched using the Maxwell area rule from the one solution on the left, which I think in the last video we called V1, to the solution on the right, which I think in the last video we called V3. That is to say, in the last video, we examined a rectification approach in which it was all or nothing. The system simply switched from a lower volume V1 to a higher volume V3 at some value of the pressure as we brought the pressure down. Here, the switchover point that we found in the last video is merely the point at which the number of liquid particles will equal the number of gas particles. But in fact, we have a smooth transition from liquid to gas. Basically, more and more particles, let's imagine that we're coming down in pressure. So more and more particles enter the gaseous phase until at this point, at the bottom of our range of interest, all of the particles are now in the gaseous phase and no more are left in the liquid phase. So this rectification approach 2, is maybe a little bit more general. It gives us a more clear physical picture, but you can see how it's much more complicated to operationalize. So I'm just giving you 2 different ways that we could think about the problem, and each will have some regime where it's applicable. But that goes through about everything I wanted to say about the van der Waals phase transition, which is a very nice, simple model that obeys a liquid to gas transition. In the next couple of videos, we'll continue to look at phase transitions, which are just super interesting and underlie so much of what we care about in modern stat mech and thermal physics. Until then, thank you so much for watching.